Okay, welcome you all again. And in the last class, we looked at what is called plain turbulent Couette flow. So we basically wanted to understand uh, what is the role of the pressure strain rate term. For that, we considered an example which is plain turbulent Couette flow, and we considered that it is fully developed. So this is the condition that we have considered. Some of you asked the question, why these two are 0? How do you know this a priori before calculating? We don't know. I will show you from the data. The results yield these two mean velocities to be 0, okay, when it comes to a fully developed condition. Okay, so we have considered a fully developed flow condition, and of course when the flow achieves statistical stationarity and homogeneous in the two directions x1 and x3. Using this, we applied to the equations, right, the Reynolds-Stress equations for 3 different directions. For x1, that is I equal to 1, k equal to 1, and I equal to k equal to 2, and I equal to 3, k equal to 3. 3 directions we applied to see what happens to the Reynolds-Stress equations, and we found that the main takeaway was that in the flow direction, that is x1 direction, right, that's where the plate is moving along the x1 direction. In that direction, we found that the production term P11 is not 0. So the production rate for U1 prime stress exists and it is non-zero. But when we applied for 2 and 3, the x2 direction and x3 direction, we find that the P22 becomes 0 and P33 becomes 0. So the production rates are 0 for the other 2 directions. Okay, so despite that, we have of course no information on what these 3 stresses look like from the equation. One must solve them or measure them to know what they are. But the equations itself are telling that production rates are there only along one direction, and the other 2 direction it doesn't exist. Okay, so now we go back to this particular flow problem to understand what we have studied so far. All right. So in this particular flow problem now, so I have taken the plain turbulent Couette flow. This is the data from my own DNS calculations. So this is in-house DNS data. In-house. We will come to that, what DNS means. In-house DNS data is what I am presenting here. So you are seeing here the first slide. Of course, here the flow is going from left to right. It's a 3-dimensional flow, right? So the configuration what we have taken is essentially, if I put it here, as I mentioned, or if I take it in 3D also, it's not complicated to imagine. There is a plate, the top one and the bottom one, 2 infinitely long parallel plates, and the top plate is of course moving along the x direction. So we can give this coordinate system x1, this I call it x3, and the x2 is the out of plane component. So this particular plate is now moving on the right side, and the bottom one is fixed. Okay. So if I do this, then I am now looking into this particular coordinate system here for this top one. This is your x1, and this is along the x1, and this is your x3. So I am taking a cut plane and I am looking into at a particular time. At some time t, I am showing you an instantaneous cut section how the flow looks like. Okay, so this is the top plate is now moving in this direction, bottom one is fixed here. So you see nice turbulent fluctuating contours. The highest velocity is of course on the wall because the plate is moving, no slip is applied there. And the out of plane, as I said, so the flow is the way I have simulated here is that it's infinitely long along the x1 direction, infinitely long along the x2 direction. X2 is the out of plane. only along x3 it is 2h. The height of the or the gap between the two plates is 2h here. Alright. So now if I look at the data after it has come to a statistical stationary state, and when it has and then I take samples and I make sure that it is statistically convergent. So this is my u1 velocity component at some time t, and what I have here is the u1 bar, this particular second graph here. So you can see here that obviously the mean data is not as exciting as the instantaneous, but the one takeaway here is that you can readily see that along the x1, this is the x1 direction, okay, and this is the x3 direction here. So you can readily see that along the x1 direction gradients are 0, the homogeneity that we talked about, right. So you have this dou u1 bar by dou x1 equal to 0, no gradients along the x1 as I walk. So whether I take data at this location or this location or this, data will look the same as long as I am going along the same walking along the same x1 walking along x1 at the same x2 x3 locations. And when I subtract the u1 minus, so I get here, this is my u1 prime, u1 minus u1 bar is this data. Obviously the excitement is back now, you see the random components here, and if I now look at the next view, which is where the flow is coming towards you, this is flow is from left to right, okay. So this is another view where the flow is coming towards you, okay. So this is basically your towards you indicates this is x3, still the wall normal direction, the gap between the two walls, and this is the x2 direction, which is the out of plane that we talked about. So you are looking into the data in the out of plane, right. It's difficult to imagine in 3D, that's why I have taken a cut section for you to see. So this is an x2 x3 plane, earlier you had x1 x3. So this is flow is coming towards you, same thing, I have this is u1 at some instantaneous, this is my u1 bar, and this is the u1 fluctuation component, okay. So yeah, again you see here this is the x2, right. So I have dou u1 bar by dou x2 equal to 0, span wise homogeneity, this is x2 is the span out of plane, so homogeneity is also visible here. So whatever we considered that the flow is homogeneous along x1 and x2 is valid, okay. Only it is inhomogeneous along x3, that is the wall normal, x3 is the wall normal direction, okay. Now this is about the statistical part. So basically each of this data here, there are like thousands of samples here, I am just plotting for you to see, and you can see each looks very different. So u1 represents instantaneous data, and this red particularly indicates that it is, I will just indicate what this means. So this is u1 bar is essentially this red colored one, okay. The red color line is your u1 bar, and this is your x2, the wall normal direction, right. I already told you it is 2h is the gap between the stationary and the moving wall. So obviously this is the moving wall, the highest velocity is here, and this is my u1 here, and at the bottom wall it is 0, it is, I have given 1 at the top wall moving there, and if I subtract each of this u1 minus u1 bar, I get u1 prime, and they are all oscillating around 0, okay, oscillating around 0. So therefore u1 prime over bar, if its ensemble average should be 0, here it should be very small value, since it is a time average here, it will be non-zero, but small decimal, maybe 10 raised to minus 3 or something like that, depending on how many more samples you can take, but it will never be 0 since it's not a ensemble mean. And this is the other velocity component, u2. So u2 is the out of plane velocity, and of course the mean is, the u2 bar is this red color again, which is 0 here. So u2 and u2 prime are essentially the same here, right, because the mean is going to be 0. We are looking into the wall normal direction. So this is your x2, sorry, x3 here. x3 is the wall normal direction. The values are 0, the mean, and this is the wall normal velocity, x3. We are looking into u3 velocity, which is the wall normal velocity. Again, its instantaneous and fluctuation look the same because the mean u3 bar is this one, the red color one. u3 bar is 0. u2 bar is also 0, like previous slide here, u2 bar. And that's what I mentioned, when the flow comes to a fully developed state, the u2 bar and u3 bar, the mean velocities, these two velocities are 0, only u1 bar velocity exists. And that's why the production rates P22 became 0, P33 became 0, because of these two velocities do not exist, and therefore there is no strain. You need strain of that velocity, right? That gradient didn't exist because it's 0 here. Now I am just looking into a contour. So this is, if I take the 3D view, the way I drew before, right? So if you have the, so this was your top wall that was moving, and the bottom wall was the fixed wall, right? So I am now cutting a section at the mid plane. So I am looking into a plane here, and then I am showing you the data, how it looks like, a mid plane or a wall parallel plane, a plane that is parallel to the walls, and I have taken somewhere in the middle of the channel height here, and this is your u1, the left hand side, right hand side is u3. So this will become essentially, this coordinate is basically your x1, and this is your x2, the span. So I am looking into all the wall parallel planes here, x1, then x2, and we are looking into u1 and u3 velocity. u1 obviously exists, so u1 instantaneous, and this is u1 bar at that particular plane. And if you see here, it looks green, but if you see, the value of green is 0.5, okay, so it's exactly at the mid plane, middle of the channel. And this is the fluctuation, this is u1 prime here plotted. On the right hand side I have the u3 velocity component, and its mean at the mid plane is 0. It's 0 everywhere basically, it's not at the mid plane. So green indicates here it is 0, and this is the u3 bar, this is the u3 fluctuation, okay. So u3 bar is 0 throughout, just to illustrate how it looks like. And you can already see from the fluctuations from the left and the right. So this is u1 prime fluctuation, and this is u3 prime fluctuation. You can see the nature of these two are different. The u1 prime is showing some elongated structures that we call turbulent streaks, and those are absent in u3 prime. They have more or less tiny turbulent eddies, but u1 prime has this red and blue elongated. Red of course indicates high speed, blue indicates low speed. So it has high speed, low speed, long structures. This is characteristics of this particular flow. So don't assume that this kind of structure exists in, if you go to a turbulent jet or a plume or something. It's a different flow. This particular flow is showing that the fluctuations u1 prime are different. The anisotropy is visible even instantaneously, even doing any statistics. So yeah, so this graph finally concludes. I am looking into the 3 RMS fluctuations, right. So essentially this is my, if I square this, I would get u1 prime u1 prime. So what I am looking into is this, right. So this is non-zero. So we didn't have data when we looked at the 3 equations. We only found that P11 is non-zero there when we looked into the Reynolds stress equation, and the stress is also non-zero, right. And then we have the V and the WRMS. In the context of what we are doing, I can just change this. This is the x3 in our notation. Okay, so this is the u1 prime, and we have this. This is the 2 u2 prime average is also non-zero. This is the out of plane component along the x2 direction, and x3 was our wall normal, which is u3 prime is also non-zero. All 3 stress exists, but P22 was 0 for this problem and P33 is 0 for this problem. So the question is, who is producing this particular stress? Okay, so the question is, who is producing this u2 prime average and u3 prime average? What terms are responsible for this? How did this come into existence? And they are not tiny, they are almost like 50% of this, and the other one is like, let's say, 1/3 of that. So they are not very, you cannot say that they are negligible or something, they are dominant. And we also see the anisotropy, that is, we see URMS or the u1 prime average, okay, is not equal to the u2 prime average. And similarly, so anisotropy, you can see anisotropy is visible even in a flow where, in the one of the simplest definition of a flow, it's not a engineering problem. Even in a canonical flow, you can see where the flow is going unidirectional, you can see anisotropy. The stresses are not equal. Okay, so now what is causing this? So we will come back to see what term is responsible for this. Okay, so the question we are asking is, what terms are responsible, or the which term is responsible for the presence of u2 prime average and u3 prime average. For that, what we do is we look at here, of course we learnt already that P22 is 0, P33 is 0. This is the scenario we have. So let's look at the pressure strain rate term itself. Okay, pressure strain rate term. What does this term look like? So we had this phi I k equal to P prime by rho dou ui prime by dou xk plus dou uk prime by dou xi average. And we of course wrote the 3 different terms, phi 11, phi 22 and phi 33, correct? So for when I equal to 1, k equal to 1, that is for the one of the stresses. Phi11 became 2 p prime by rho dou u1 prime by dou x1 average, and Phi22 was 2 p prime by rho dou u2 prime by dou x2 average, and Phi33 was 2 p prime by rho dou u3 prime by dou x3 average. Okay.